So here we go. If you see the solution, you get all these. There's no need to watch this video. But if you want to kind of talk, hear me talk our way through this, feel free to watch. So we got a lot of vocabulary terms, and they're very similar to one another. So let's be very careful. Notice a couple of things here. Electric potential difference, voltage. Those two are synonyms of each other. Electric field strength is a synonym of electric field intensity. Okay, so there we go. The rest are unique. So the work done, So work has got to be something about change. Per unit charge to move through an electric field, that is voltage, right? Because that's potential difference. Because work is about change, voltage is about change. At any point where multiple fields are present, the vector addition of the individual fields yields the net field. That is, of course, the law of superposition. Okay. The set of vectors that indicates the direction of positive particle, right? Okay, that's important. Would take, and so that is going to be the electric field. Notice it's not the electric field intensity because we're talking about the set of vectors, not like the numbers that go with them. And it's not the electric field line because that's not the set of vectors, that's just a single one of them. That's the electric field. Two equally but oppositely charged conducting metal plates separated by an insulator. That's our parallel plate capacitor, PPC. There we go. The energy per unit charge at a location in space. Now that is going to be, now notice here, there's going to be a temptation to want to say electrical potential energy, but it's not because it's the energy per unit charge at a location in space, not an actual amount of energy. So this is electric potential. The path of positive, that's an electric field line. Okay, the force per charge, right? That was our definition. So, I mean, oftentimes it helps us to write out what the equation is in the same way that this is energy per charge. Well, that's the electric potential. Here, this is electric field strength. Okay, the change in electric potential energy per change in position, that is the definition of a gradient. So that's the electric potential gradient. Now, technically, I could have said electric field strength here as well. And I could have said potential gradient here as well, except that because these two things are identical to one another in terms of their magnitudes, but look at the way these are phrased. Clearly, they're trying to point at these things specific. A small unit of energy, that is the electron volt. It is 1.6 times 10 to the negative 19 joules, right? A volt is not a unit of energy. It's a joule per coulomb. It's not a joule. Right? That's like saying lemons cost 4 lemons for $1, right? How many lemons do you have? You have no lemons. You just know how much they cost for $1, right? So you have no energy if I just know the number of joules per coulomb. I don't have energy unless it's just joules or electron volts in this case. So it requires no work for a charge to move along at a constant speed. That's an equipotential surface, right? A surface along which something can move without changing potential energy, right? Notice work is equal to Q naught delta V. On an equipotential surface, delta V would be 0. The capacity of a charge in a field has to affect the environment. So already we've got capacity to affect the environment, that's energy. And because it's the location of the electric field, that's why I know that that's electrical potential energy. All right, cool. Page 2. So where would you place a plus 7e charge to have the most electrical potential energy? Remember, so my source charge at the center is a positive, okay? That means wherever it would have the greatest falling distance. So since a positive charge is going to go away, I want to get it as close in because C would have the furthest to move. Now, granted, they all go to infinity, so let's not try this infinity math. To infinity, this is infinity plus a meter, and this is infinity plus 2 meters, but it's still a larger one. It might not make a big difference, but it does make a difference. So this is at position C. And if I have a negative 12e charge, so I have the most electrical potential energy, since that would fall inwards, I would need the outermost shell here, so A. What is the voltage between? Right, remember voltage is just the difference. Because voltage is electrical potential difference, delta V, A to B. So A to B, if we look down here, the ring, technically this should be, therefore, it would matter actually if we're gonna talk about going from A to B or B to A, but since I don't care about that, I'm just doing the magnitudes, right? And we're not dealing with all the sign conventions. This is just the 45 volts minus 30 volts, or 15 volts is the voltage between. Between B and C, same thing. This is just the magnitude of 45 volts minus 90 volts, and that's 45 volts. B and D, where's D? D's over here. Oh, they're on the same equipotential surface. 45 volts minus 45 volts is 0 volts. There's no potential difference between those, A and D. It's not like you go this way and then that way. I can just sort of like, boom, there. It doesn't matter what the path is. So let's actually talk about that. Why does the path not matter? The path does not matter because the electric force is conservative. And when you have a conservative force, the whole concept is the work is path independent. And we said that before, a long time ago, but we did say it. So between A, which has a potential of 30, and D has a potential of 45, that is 15 volt potential difference. So how much work in electron volts would it take to move an electron from A to B? Great, work is equal to Q naught delta V. We're just ignoring all the signs in electron volts. So I want to do my charge in elementary charges then. 1E, A to B is 15 volts. That's 15 EVs. And work in electron volts to make it 20 from C to D, right? So work is equal to Q naught delta V, and therefore it's 20E and delta V from C to D. Did we do that one? C to D. Oh, we didn't do that one, so it's a new voltage. C to D. C is 90 volts. D is 45. So the potential difference there is 45 volts, and that's going to be 900 EVs. And so there you go. Now, I did want to make one mention here. I want you to notice something here about the potential gradient, right? Remember that the potential gradient is the change in potential per unit displacement. So notice here, go from this shell to this shell. It's a 1 meter move, and it's a change of 45. So 45 volts over 1 meter is 45 volts per meter. Okay, notice here it's the same distance, but now we have a 15 volt change over 1 meter, and so that's 15 volts per meter. So what's happening there? Well, in this region, the potential gradient is not constant. In other words, it would take more work to move from here to here than it would from here to here. Well, why is that? Oh, okay. Well, let's remember what we said about potential gradient. Potential gradient is the same thing as the electric field strength. Oh, now this makes a lot more sense because look, when you're closer, the electric field is stronger than when you're further, right? So because in this space, the electric field is weakening as you go outwards, it makes sense that the potential gradient is getting less as well. Whereas in the parallel plate capacitor, because the electric field was constant, so was the potential gradient. So there you go on that.